Hello, in this lecture we are going to talk about forces, Newton's laws, and try to understand why things move the way they do. But before going on and learning the new chapter, let us first revisit the idea of projectile motion and see if we can connect the concepts of projectile motion to the new concepts of forces that we are about to learn. So we have seen this kind of diagram or this kind of trajectory a lot, hopefully, when solving projectile motion problems. So here we have two balls A and B, A with the blue trajectory and B follows the pink trajectory. We see two features from this graph. One is that they both seem to have reached the same maximum height. However, the pink trajectory has a longer horizontal distance covered and then the blue trajectory. Okay? So we ask ourselves, which of these projectiles reach the ground first? Let's investigate the two features of these trajectories and try to get to the answer. First, how does the two projectiles have the same height? So we know that height is a vertical variable, so it is determined by other vertical variables. The first thing that we know is, which is the same for any projectile moving near the surface of the earth, is acceleration due to gravity, which is a vertical acceleration and the only acceleration for any projectile motion. So we can understand that since both A and B experience the same constant vertical acceleration due to gravity, that means the time should be determined by vertical motion only. Time should be determined, must be determined by vertical acceleration felt by projectiles, because as we know, in the horizontal direction there is no acceleration, so nothing to impact its time of flight. Okay, so another thing that we must be sure of, here we have two things that are same for both A and B. One is the acceleration due to gravity, which is the same for any projectile, and then two is they have reached the same maximum height. Since they have reached the same maximum height, that should also mean that they would both reach the ground at the same time. Why? Because reaching the same maximum height would imply that you have three vertical components that are the same between the two projectiles. Two of them we have already seen, acceleration due to gravity and maximum height. The third thing would be its vertical component of velocity. If these three things, vertical component of velocity, acceleration due to gravity, and the maximum height attained by two projectiles are the same, their time of flight must be the same. So, does the range difference or the horizontal displacement covered by both A and B being different, does it have any impact? Well, this means that the range of a projectile is determined only by horizontal variables. What are the horizontal variables that we know? We know that there is no acceleration in the horizontal direction, and so there is no change in the initial velocity in the horizontal direction, because there is nothing to change the velocity. Acceleration is defined as the change in velocity. Hence, longer range or longer horizontal distance just means that you have a larger horizontal component of velocity for the one with the bigger range. So here B, the pink curve, seems to have the larger horizontal component of velocity, which determines the larger range of the projectile. It doesn't determine time of flight. Okay, so in summary, both A and B must reach the ground at the same time, because time of flight is determined by vertical motion, and if two projectiles have reached the same maximum height, since they feel the same acceleration due to gravity, it must be so that their initial vertical velocity components were equal. In answering this question, we have seen that a kinematic answer tells us how these things should move for them to have the same time of flight. That is the topic of kinematics that we have learned so far. However, we want to know in physics also why things move. Why things move is answered by the study of dynamics. Dynamics include the concept of forces and Newton's laws that we are going to get into today. So if we ask what forces is, it is impossible to get around the fact that forces were first fully explained by Isaac Newton with his 3 laws of motion. Those 3 laws of motion actually tells us or explains to us why things move the way they do. Okay, so what is the first of these 3 laws? The first of these 3 laws, the first law, states that an object at rest will stay at rest while an object moving with constant speed in a straight line will continue moving in that manner until and unless it is acted upon by an external force. Now, there is a lot to digest in this statement. What this law is essentially talking about is the tendency of objects to retain its state of motion. The state of motion of an object is, for example, if an object is speeding up or is not moving at all or moving at constant speed. So these are the states of motion, and an object tends to retain its state of motion until and unless we have exerted an external force on that object. For example, what can that force be? Well, that force can be something like when you're driving on the highway, say your speed is 70 miles an hour, constant speed, you're not changing it, you're just cruising. Then all of a sudden, if you see that the traffic has slowed down and you have a commotion up ahead, then basically what would you do? You would have to put your feet on the brake and bring the speed down. So there's a braking force which will act as the external force to change or alter the state of motion of your car. Okay, in that it will cause the car to slow down. Okay, before, if you hadn't put on your slammed on your brakes, then the car would still be moving at the constant velocity of 70 miles an hour. Okay, so what are the main implications of this statement? Well, anything at rest will stay at rest. So if there's a book on your desk, that book will stay at rest forever until and unless you decide to move it. Anything moving at constant speed in a straight line, which is just constant velocity, will continue moving in that manner, as we talked about the car example, unless we have a force or an external force that is acting on those objects. In this case, when the book is at rest, you may pull it up. You may put it somewhere else by dragging it off the desk. Those are external forces. So we see 2 scenarios. Here, an object at rest, say the book. At rest means nothing is moving, so of course there is no acceleration. When your car is traveling at a constant speed in a straight line, that also means no acceleration, because acceleration is defined as the change in velocity over time. Constant velocity means 0 acceleration. And so we can say that when you're slamming on your brakes, you're making the car decelerate, right? That means when you are changing the state of motion of your car from moving at a constant velocity to maybe coming to a stop or slowing down, you're imposing or you're causing an acceleration. So acceleration is a requirement if you are to change the state of motion of an object. And how do we bring about such an acceleration? For the car example, we are slamming on our brakes. So we can say that braking force is causing the deceleration, right? So in essence, forces are the cause of acceleration. Let's look at a familiar example to understand what is actually happening with Newton's first law. So let's revisit the example we saw earlier in the lecture. We have two projectiles being projected at different angles, but they reach the same maximum height covering different horizontal distances. As we know, in projectiles, the only acceleration is due to gravity, which is vertically downwards, and there is no acceleration in the horizontal direction. The vertical acceleration, this just means that there is a vertical force acting on the projectiles, which we know as gravity. Okay, so gravity is the force that causes the vertical acceleration, which causes any projectile going up to come back down. Okay, so that is why, since an external agent, an external force is acting on your projectile, that force will determine the time of flight. While in the horizontal direction, since there is no acceleration, there is no force, even though the time of flight for these two projectiles is the same, their horizontal distance can be different because horizontally there is no acceleration, horizontally there is no force, and so their constant velocity remains the same. So whichever projectile has the bigger horizontal component of velocity will cover the further horizontal distance. Now let us get into the nitty-gritty of it. What is a force? Okay, so very simply, force is a push or a pull. This is a very naive definition, but it works. Also, we can say forces are actually interactions between different objects, or specifically between two objects. All right, so these kinds of pushes, pulls, interactions, whatever you choose to call them, these can be of two types. So forces can be of two types. One of them is contact forces or short range forces. For these forces to exist, there must be physical contact between two objects. For example, when you're walking on the road and your feet is touching the road surface or the pavement surface, which means there's contact between your feet and the ground. There is a force between you and the ground, whether it be friction or any other kind of force, we'll investigate later. So any two objects touching and exerting forces on each other, so interacting by touching, is what we call contact forces, and they're short range forces in that they can only occur when two things are physically in contact. Contactless forces, on the other hand, they are long range forces, so they can exist between two objects without any physical contact. The best example for contactless forces is gravity. So for gravity to act on me, I don't need to be in contact with the ground, because if I jump, I come back down, which means even if I lose contact with the ground, gravity is acting to make me fall back downwards. Another example may be electromagnetism, but not for this course. We will only study gravity as the only contactless force in this course. So what are the requirements for certain forces? So one of the main requirements is we must have two things to be interacting for there to be a force between them. So force can be thought of as a communication language between two things interacting either via physical contact or no contact at all, like when something is interacting with gravity. So force is an invisible reality that exists between two objects interacting via contact or via gravity. Multiple forces can also act on the same object at the same time. For example, when I'm just standing giving this lecture, I have multiple forces acting on me. Very simple example would be gravity always acts on me, which gives me my weight. So I have gravity. I'm standing on the ground, which means there's a force between me and the ground, which is enabling me to stand. So that shows that I have at least two forces acting on me, one due to gravity and one from the ground. Okay, so multiple forces can act on me at the same time. And when I'm walking, I have friction with my feet and the ground. So now there are three forces. Okay. However, for things to be accelerating or for things to change their states of motion, what is important is the net or resultant or total force. Okay, when that net force on an object, net means summation, when the summation of all forces in an object is greater than 0, then acceleration would be greater than 0. One of the main properties of force is it is a vector quantity. So again, when summing vectors like we did in projectile motion, we have to be very careful about summing x components to x components, or x forces to x forces, y forces to y forces, and so on and so forth. Okay, and then we'll use our general vector addition rules like Pythagoras theorem and tangent theta to find direction of forces. Okay, since force is a vector, we have to be very careful about how we choose to add vectors. So like any other vector, the first thing to do would be to draw a very clear diagram. So this diagram is kind of different from the diagrams that we have been drawing so far, like in projectile motion. In projectile motion, you would see we would draw out a simple version of the actual situation that is happening, the actual scenario, with all the quantities in it. So the initial velocity, the acceleration, and so on and so forth. However, this kind of diagram, which we use when summing forces, or which we use in any force problem that we'll ever come across, or any problem in general, you can basically draw this diagram showing the forces on it, on an object, is called a free body diagram or free body force diagram, FBD. So what is this? How is this different? Well, you would take the object in question and just that object, and then draw all the forces on it. So since we know forces, multiple forces can act on a single object at the same time, so we can take that object and draw out all the forces on that object in a free body diagram. How would that help? This would help in knowing which forces are in the vertical direction, which forces are in the horizontal direction, and so would help us find the total force in the x direction, or the net force, and the total force in the y direction, net force in the y direction, and then the total force in general, like by forming a vector triangle like we did in also projectile motion, right? All right, let's look at an example. So we have a book sliding on a desk and we want to draw the free body diagram. So our purpose here is to draw a free body diagram for book. Okay, so the object in question is my book. So the free body diagram for the book will only have the book. Okay, and then what are the forces acting on it? Anything with mass will have a weight on Earth and anywhere where is gravity, where there is gravity. So the first force we will draw is from the center vertically downwards for any object with mass. Okay, this will be the weight W or Fg, force of gravity, or you can just write m times g, because as we know, weight is nothing but mass times the acceleration due to gravity, g. Okay, so the first force is the weight. What is the second force? Since it's on a table, so two surfaces are interacting, two surfaces are physically touching, that means there is a force that exists between the desk and the book. So since the book is not falling through, this means the table or the desk is upholding it. So by exerting an upward force, which we call the normal force or the contact force, and we will talk about these more as we go forward. Okay, now this is the normal force which is provided by the desk on the book to keep it upright and on the desk. Okay, so this is a contact force. This is the weight, which is a contactless force due to gravity. All right, and then the book is also sliding on a desk. So any desk in real life, if you rub your hands across your own desk, you will feel a resistance to your sliding motion of your hand, meaning there is friction between your hand and the desk. So any real desk in the world will have that friction. So since the book is sliding in the rightward direction, the friction that exists between the book and the desk will act to oppose this sliding direction or sliding motion. So in other words, acting to the left. Now if you want to add these forces, you would have to first, like any other vector problem, choose our axes. We can choose this to be positive, this to be positive x, this to be positive y, and then add as follows like we did previously. But let's not get into it here. We'll learn about these addition of forces later in the chapter. Let's look at a second example. So let's say we have the same book, but then we have a tilted surface or an inclined surface. Okay, a surface which is inclined. The book is here. Okay, so we can think of intuitively that the book will slide down the slope, right? This is basic intuition, and we'll learn more when when we go deeper into the chapter. But for now, let's just think it is intuitively just sliding downwards. Okay, so it is sliding down along the slope. We want to draw the free body diagram for this book now. How is it different, or is it different from that diagram? So we have the book on an incline. So what are the forces on it? Again, it has mass, the same book we're talking about, so it must have gravity acting on it, so it must have a weight. That weight will always be vertically downwards. Okay, so from the middle point, take an arrow pointed vertically downwards. This is your weight. Okay, now it is in contact with an inclined surface. The surface of this kind of table is now interacting with the book, but in a different orientation than before. But whenever there is contact between two surfaces, there must be a force which is acting between the two surfaces. That force, as we will learn, is always perpendicular to the surface. Okay, so that force will be, now the normal force will be directed this way. Okay, why? Because it is forming a right angle with the surface. Okay, and we'll learn more about them later in the chapter. Since it's sliding down the slope, right, down along the slope, our friction will now be up along the force, up along the slope. Okay, basically friction is a force which is opposing any kind of sliding motion, whether on an incline or on this desk, okay, on a horizontal desk. So these are some of the ways that we can draw free body diagrams for different objects in different orientations. Hope this makes sense.